using correct units, explain the meaning of v prime of 3 equals 84. Well, this used to be my favorite notation, but now I've decided that when I want to do an interpretation question, v prime of 3 equals 84, I normally change that to dv dt because we're looking at how velocity changes over time at t equals 3 is equal to 84. So when I would interpret this as when t equals 3 seconds, when t is equal to 3, the velocity, we'll look at the numerator, is, well, it's changing. How is it changing? This is the rate of change. So it is increasing at a rate of 84. Now let's pay attention to the units. 84 what? The velocity is being measured in meters per second. What's time being measured in? Also being measured in seconds. So when t equals 3 seconds, the velocity is increasing at a rate of 84 meters per second. Done. All right, our next bullet point. What is the velocity of the particle when the acceleration is first equal to 0? So I need v of t when the acceleration is equal to 0. Well, what's the acceleration? I think we already figured that out in this last problem. The acceleration is the same thing as v prime. Where is v prime equal to 0? We found that v prime would be equal to 0 at t equals 2/3 and at t equals 2. We want to know the velocity when the acceleration is first equal to 0. Well, that's going to be here. This is the first time a of t equals 0. And so we need to know the velocity at that point. So we need v of 2/3. I'm going to cheat and just leave that to you to figure out. But how are you going to do that? You're going to go back to your velocity function, and everywhere you have a t, you're going to replace it with 2/3. So that'll be 12 times 2/3 cubed minus 48 times 2/3 squared plus 48 times 2/3. Oh, I feel really badly. Let's finish that off. 2/3 cubed is 8 over 27. 8 over 27 times 12 is 96 over 27. Minus 2/3 squared is 4/9 times 48 is 192 over 9. Plus 48 times 2/3 is 96 over 3. 96 over 27, I can make that 32 over 9. Minus 192 over 9. Plus we'll make that 288 over 9. 32 minus that's negative 160, plus that should be 128 over 9, and that will be meters per second. So the velocity when t equals 2/3 will be 128 over 9, which is like 14.22222 repeating on your calculator. All right, time to land the plane. We're going to bring this baby home. Shown to the right is the velocity of the particle on the time interval -5 to 5. I don't actually want it on the time interval -5 to 5. I just want it on the time interval 0 to 5. So we're not going to consider this part of the graph. Just scratch that off. Using this information, sketch the graph of the acceleration. Well, if that's your velocity function, well, what do we know about acceleration? Acceleration is the derivative of the velocity. So let's go back to an earlier conversation. If I'm going to look at the derivative of the velocity, easy points for me to consider right here. We know that the derivative is equal to 0. Over here, the derivative is equal to 0. Over here, my derivative is, my velocity is increasing, so the derivative is positive. Over here, the velocity is decreasing, So V prime is negative. This guy is increasing. V prime is positive. So I need a graph that is going to be positive, then 0, then negative, then 0, then positive. So if I was to sketch that, I'm going to use a different color for that. For this value of time, the acceleration is equal to 0. For this value of time, the acceleration is equal to 0. I need my acceleration to be positive, so above the x-axis, then negative, then positive. And so I want something that looks like that. That brown graph will represent my acceleration. It doesn't have to look exactly like that, just something like that. And where I'm going to look is, does the acceleration have a root when the velocity has a maximum? Does the acceleration have a root when the velocity has a minimum? Is the acceleration negative when your velocity is decreasing? And is your acceleration positive when the velocity is increasing? Those are all the things I'm going to be looking at. Now for the last part. And this is not something we've talked about yet. It's something I hope to talk about in class on Friday, if we're lucky. Okay. So using the graph of the velocity, I want to generate the graph of the position. Now here's the tricky part. If what I have is the velocity, well, I know the velocity is related to the position. How is it related? The velocity is the derivative of the position. Another way to say that is that the position is the antiderivative. It's the antiderivative of your velocity function. And that's going to be a little tricky for us, but let's see what we can do. We're told that x of 0 is equal to 3. So if I am generating a graph, I'm going to say that this is the point 0, 3. The brown graph represents the graph of my position. Well, what is the particle doing? If I pay attention to the velocity is positive. If my velocity is positive, what does that mean for my position? That means that my position, since this guy here is positive, my position is going to be increasing. Over here, I hit a relative max. My velocity is still positive. So I go from positive, relative max, to still positive. My velocity is equal to 0 here, and then I continue to have a positive velocity. So my graph is going to have to do this. Positive velocity means acceleration is increasing. So I'm increasing until I reach this point where I'm at like the maximum. And let's see, then I need to continue increasing. All right, so I do that until just about over here. And then I need to increase yet some more. So we increase. Wow, that's a really bad example for us to be looking at. And I'm probably going to delete this from the video. If I don't delete it from the video, just delete this from your memory banks. This was not a good example. My apologies.